Full wave bridge rectifier circuit consists of 4 diodes. So if you compare this circuit with the previous circuit, then it does not involve any kind of transformers. And due to that, the size of this circuit will get reduced. Alright, so now let us see the working of this full wave bridge rectifier. So if we apply the sine wave as an input to the circuit, then during the positive half cycle, this diode D2 and D4 will conduct, while this D1 and D3 diode will remain off. So during the positive half cycle, the current will flow through this path. And if we assume this diode D2 and D4 are ideal, in that case, this input voltage will appear across this load resistor. So the same input voltage will also appear at the output terminal. Similarly, during the negative half cycle, these diodes D2 and D4 will remain off. And on the other end, this diode D1 and D3 will conduct. So during the negative half cycle, the current in the circuit will flow in this way. And if you observe over here, during the negative half cycle also, the current which is flowing through the load is in the same direction. So during the negative half cycle, we will get this kind of waveform. So if we combine the positive as well as the negative half cycle, then we will get this kind of waveform. Now, if we consider these 4 diodes as an ideal diode, in that case, the average value of the full wave rectifier will be equal to 2 Vm divided by pi. But if we also consider the voltage drop across this diode, in that case, the average value can be given by this expression, that is 2 times Vm minus 1.4 divided by pi. Or in general, we can say that the average value will be equal to 2 times Vm minus 2 Vt divided by pi, where Vt is the forward voltage drop across these 2 diodes. And here in the waveform, this T dash is the new time period of the output waveform, where T dash is equal to T by 2. Alright, so now let us find out the peak inverse voltage for this full wave bridge rectifier circuit. And to find the peak inverse voltage, let us assume that during the positive half cycle, this diode D2 and D4 are conducting, while this diode D1 and D3 are in the off condition. So in that case, like we had seen, the current will flow in this fashion. And in that condition, let us say the reverse voltage which appears across this diode D1 and D3 are Vd1 and Vd3 respectively. So if we apply the KVL in this particular loop, then we can say that this Vd1 is equal to V0. And here we are assuming that the all 4 diodes are ideal diode. So in that condition, the same input voltage will also appear across this load. That means we can say that this Vd1 will be equal to input voltage, and the peak value of the input voltage will be equal to Vm. That means the peak inverse voltage which will appear across this diode D1 will be equal to Vm. And the same is true for this diode D3. So if we apply the KVL in this loop, then we can find that this Vd3 will be equal to Vin, and the peak value of the reverse voltage will be equal to Vm. So for the full wave bridge rectifier circuit, this peak inverse voltage is equal to Vm. So far we have seen that how we can design this full wave rectifier circuit using either center trap transformer or using the bridge rectifier circuit. But if you observe this output waveform, it is not completely DC voltage, because still there is some periodic variation in this output waveform. So this periodic AC variation in the DC output voltage is known as the ripple. And this ripple can be reduced by using the filter circuit at the output of the rectifier. So as shown in the figure, by using the filter circuit, we can minimize the effect of ripple. So with this filter, if you see the output waveform, then the output waveform will look like this. So this blue waveform is the waveform just before the filter, and this yellow waveform is the output of this filter. So with this filter circuit, how well this ripple is removed, it depends on the value of this load resistance RL as well as this capacitor. So before we see that, first of all let us understand how this filter circuit works. So during the positive half cycle, this capacitor will get charged up to the peak voltage. And once this capacitor gets fully charged, then this diode D1 will become reverse bias. So after the peak voltage, this capacitor gets discharged through this resistor RL. And due to this discharge, we will get this kind of waveform. So once again, this capacitor starts charging whenever the voltage across the capacitor just go below this input voltage. So after that time, once again, this diode D1 will start charging through this path. And once again, when the voltage across the capacitor will become Vm, then this diode D2 will become off. And once again, now this capacitor starts discharging through this resistor RL. So due to the charging and the discharging of this capacitor, we will get this kind of waveform. So in the circuit, how well the ripple is removed, it depends on the RC time constant of this filter. So for the better rejection of this ripple, the RC time constant should be much larger than this time period. So suppose if this RC time constant is less than this time period T dash, in that case, this capacitor will get discharged rapidly. So due to that, we will get a more ripple in the output waveform. So to avoid that, this RC time constant should be much larger than this T dash. But still, if you observe, there is some ripple in the output waveform, and this ripple voltage is known as the peak to peak ripple. So if Vm is the peak voltage and this voltage is the peak to peak ripple, then this peak to peak ripple can be given by this expression, that is Vm divided by 2f times RL times C, where here f is the frequency of the input signal. So if we consider the frequency of this output waveform, then this 2f should be replaced by this frequency f dash. Now for this waveform, suppose if you want to find the DC voltage, then this VDC can be given by the expression Vm minus V peak to peak ripple divided by 2. That means if this voltage is the peak to peak ripple, then the DC voltage will be the subtraction of this Vm minus half of this ripple voltage, and that will be the approximate DC voltage of this output waveform. So this will be the expression of a DC voltage after the filtration. And here if we assume that this ripple voltage is much less than the peak amplitude of the sine wave, in that case the approximate value of this DC voltage will be equal to Vm. Now this ripple voltage can also be expressed in terms of the load current, that is IDC divided by 2FC. So anyway, we will derive all these expression in the separate video. So using this rectifier and the filter circuit, we can reduce a ripple in the output waveform. And how well this ripple is removed from the circuit can be defined by the parameter which is known as ripple factor. So this ripple factor is the ratio of the RMS value of this ripple divided by the DC voltage. And for the full wave rectifier without any filtration, this ripple factor is equal to 0.43. Now if you recall the ripple factor for the half wave rectifier, it was equal to 1.21. So for the full wave rectifier circuit, the ripple factor has been improved drastically, and it can be further improved by using the filter circuit. So for the full wave rectifier with the filter circuit, the ripple factor can be given by this expression. So we will derive all these expressions in the separate video. Now one more parameter which is defined for the full wave rectifier is the efficiency, that is how well the AC input power is converted into the DC power. And for the full wave rectifier, this efficiency is equal to 81.2%. And if you recall, for the half wave rectifier, the efficiency was 40.6%. So using the full wave rectifier, we can almost double the efficiency. So in summary, here is the different parameters which we have discussed so far for the full wave rectifier, and these parameters are also defined separately for the center tape as well as the bridge rectifier circuit. Now out of all the parameters, some of the parameters we have discussed very briefly, but in the separate video we will also derive all these expressions. So I hope in this video you understood how we can design a full wave rectifier circuit using the center tape transformer as well as using the bridge circuit. So if you have any question or suggestion, Do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.